world, but the mechanism is not really understood by classical physics. Then we can think quantum physics could help to understand and trigger it. So I carried out with Andrew Monenberg a study using relativistic quantum equations like Dirac equation to predict electron deep orbits, EDOs, called Anomalies solutions, of order femtometer range and binding energy near 500 keV. Their interest for cold fusion is to increase the electron density between hydrogen atoms with EDO, what facilitates the fusion. This study was published in chapter 16 of book Cold Fusion, edited by Jean-Paul Biberian. Moreover, according to the study made for ICCF 22 conference, the EDOs are highly relativistic. We have a relativistic correction of Coulomb potential V, giving an effective potential energy of order gamma V. The relativistic coefficient gamma, computed from reduced quantum wavelengths, and the radius ρ of EDO can exceed 200. We want to evaluate a population of EDO states while considering two antagonist interactions when gamma increases. The attractive effective potential becomes stronger, reducing the confinement radius ρ, but the Heisenberg relation increases the kinetic energy, prevent confinement. We denote this last effect Heisenberg barrier. We use the tunneling WKB method in dimension 1, similarly to the computation of Gamow astrophysical factor. The curve of K can illustrate the Heisenberg barrier, and the blue is the integral of K. The computation provides the probability of EDO states created from the ground state. Note the tunneling effect is extended here to a dynamic barrier. In fact, we obtain a quantum superposition of EDO state and ground states. The coefficient of EDO state seems very weak, but thermodynamics allows us to hope for better results. If the temperature increases, the thermal agitation of atoms increases the tunneling. In complement to the role of EDOs, cold fusion can be facilitated by the creation of superabundance vacancies, the use of catalytic materials, and high temperature of over 2000 degrees. Second part.
I have to do the second.
Second. Comment je fais prochain?
Je vais le faire. Je vais essayer.
C'est deux là. Second part, yes. Relational interpretation of fundamental quantum physics. Quantum physics was initially developed to understand chemistry and behavior of atoms, but it was quickly very fruitful in all areas of fundamental science and technological advances. The theory will predict strange phenomena never observed before, such as entanglement. In fact, for a century of existence, it has never yet been found guilty. At the beginning of the 20th century, there are still many questions about atom and its electrons. In 1913, Niels Bohr developed an atomic model similar two planets revolving around the Sun. First, for hydrogen with unique electron, then generalized to the case of relativistic electron by Arnold Sommerfeld. But does an atomic electron really have a circular or elliptical trajectory while it is supposed to jump from one orbit to another with absorption or emission of light? In fact, a beginning of quantization appears for the angular momentum of the electron, and the concept of a trajectory, more and more suspect, will abandon in favor of that of observable quantity by several physicists such as Wolfgang Pauley, Werner Heisenberg, and Niels Bohr. Then, peut-être je faut revenir. Yes. Then Heisenberg, considered as the creator of the new theory, undertakes to represent by tables called matrices the position and change of electronic orbits according to the rules. The discontinuous aspect of orbit jumps is already an introduction to concept of quantum. By calculating the energy of electron based on frequency and amplitude of the light emitted during an orbital jump, Heisenberg found those predicted by Bohr and observed experimentally. This supports the matrix model called matrix mechanics. In fact, the calculations not detailed here are similar to those used in classical physics, apart from an equation expressing the matrix product is not commutative. It uses complex numbers and a physical constant called Planck's constant, not h, which will be the signature of quantum physics. So Max Planck is considered as one of the fathers of quantum physics. At this stage, the theory seems successful, but we still do not know how the electron moves. Later, Erwin Schrödinger found the energy produced by Bohr, but in a different way. From the work of Louis de Broglie, where all matter corresponds to the wave, he builds an equation providing a wave reaction psi associated with any atomic electron. So he founded a new theory, the wave mechanics, and showed his theory is mathematically equivalent with that of Heisenberg. Moreover, he solves the mystery of trajectory of the electron. It's simply a wave diffusing in space. However, it's clear an electron bound to its atom does not diffuse in space. Then what is the purpose of the wave function? Finally, Max Born discovers the wave function allows us to calculate the probability of presence of electron at a point in space. No. We come to a question that has led to much controversies. The indeterminism of measurement and quantum theory. No certainties, only probabilities. Einstein is against that and pronounces his famous sentence, God does not play dice. Thinking the theory is incomplete, he proposes the existence of hidden variables. Moreover, with the Russian Boris Podolsky and the American Israeli Nathan Rosen, they designed a Fuchs experiment, the EPR paradox, to refute the interpretation of Copenhagen School. To simplify, this experiment cut complex is based on correlations of measurement between integrated objects. See the slide 12 done. But finally, hidden variables and EPR are invalidated while observing the valuation of Bell inegalities. The theory of quanta seems then Max Planck and Einstein discovered the energy is granular, made up of quanta determined by the Planck constant. Then, after the discovery of the photon, Einstein discovers the photoelectric effect and obtains the Nobel Prize. The theory of quantum sounds very abstract and complex, and the relational interpretation seems the best way to express how it works. In this interpretation, a property is relative, being associated with an interaction between two objects. But relational interpretation allows us two things to be true in the same time. This expresses a quantum superposition of two situations. It is illustrated by the famous paradox of Schrödinger's cat, described in a softened form for the lover cats. The cat may only be awake or asleep, and not dead. We analyze two possible and temporal evolutions to check if they are not contradictory. But the relational interpretation easily shows that the two modes of evolution applies correctly to both different situations. Here we summarize main characteristics of the theory. We consider the strangest situation that can be created by the theory an entanglement, and we show what its consequences still do not seem to be rationally explainable. But finally, thanks to relational interpretation, we can show this phenomenon is not a paradox and has its own logic. Stern and Gerlach experiment on the action of a variable magnetic field in space on a flow of silver atoms highlighted yet another strange phenomenon. These atoms do not rotate on themselves, but experience seems to show that they rotate. At first, this gave ideas to the physicists who wanted to understand this paradoxical effect. Finally, this semi-rotation was considered as an abstract observable, the spin, of considerable importance. It allows in particular to distinguish at least two types of objects: fermion with half-integer spin, elements of matter, and boson of spin integer, particles mediator of interaction. The relational interpretation allows us to have a particular approach to the concept of information, without link to thermodynamics and the notion of entropy. It simplifies the statement of properties of information as the concept of relevant information and the obvious link between measurement and information. We recap here the famous relation of indeterminacy of Heisenberg. Moreover, it's important to point out the informational product of two measurements is not commutative. In the following two slides, we analyze the two best known hypotheses to try to restore determinism illustrated in slide 10. That of many words by Hugues Havret, that of hidden variables by Louis de Broglie and David Bohm. Quantum theory remains deeply mysterious, with phenomena difficult to explain clearly. But the most incredible thing is that we can concretely exploit these phenomena. Quantum physics is not only at the origin of the most modern technologies, laser, computers, nuclear power plant, but also gave birth of a lot of theoretical and applied works grown by Nobel Prizes. It's in fact the greatest scientific revolution of all times. Here we give a non-exhaustive bibliography about quantum physics and the quantum field theory not indicated here. Thanks for your attention.
So, thank you, Jean-Luc. The floor, if you have questions.
Je veux dire encore quelque chose.
You want to add something after the thank you? Okay, go ahead.
I went to say something corresponding very recent research for me. I decided to define theory of cold fusion because I read on the forum of the cold fusion there is no theory, etc., etc. But I think it's not possible to speak about some things. We have made a very tough scientific theory. I create a theory of cold fusion, not yet reviewed, but defined by means of relativist quantum physics. I finished.
Okay, thank you. Okay, if you have any question.